What if I told you that Belgium 3D printed hundreds of artificial reef structures and placed them on the North Sea floor, creating thriving underwater cities for marine life in a place where nothing could survive? It sounds like science fiction, right? Well, Belgium actually did this. And the result after 7 years amazed the entire marine conservation community. This is that incredible story. Picture Belgium's North Sea coast, a stretch of water bordered by one of Europe's most densely populated and industrialized regions. For centuries, these waters supported abundant marine life, oyster beds covering thousands of hectares, mussel reefs stretching for kilometers, cod and plaice populations feeding millions. But by 2015, the underwater landscape had transformed into something unrecognizable. Vast stretches of barren seafloor, devoid of complex structures, supporting minimal life. The transformation resulted from decades of intensive bottom trawling, fishing techniques that drag heavy nets across the seabed, pulverizing everything in their path. This fishing method, while economically profitable short-term, proved ecologically catastrophic. Studies estimated that bottom trawling destroyed 90% of natural reef structures in the Belgian North Sea between 1950 and 2010. What remained was essentially underwater desert, flat, featureless sediment supporting drastically reduced biodiversity. The numbers painted a grim picture. Marine biodiversity in Belgian waters declined by 75% between 1970 and 2015. Commercial fish stocks collapsed. Cod populations fell by 92%, plaice by 68%. Native oyster reefs, which once covered 400 square kilometers, had completely disappeared by 1995. The few remaining species were mostly short-lived opportunists, adapted to disturbed environments. Complex food webs supporting diverse marine communities had simplified into impoverished systems, dominated by just a handful of hardy species. Economic impacts were severe. Belgium's fishing industry, which employed 15,000 people in 1970, had contracted to just 3,500 by 2015. Annual catch values dropped from 120 million to 45 million, a 62% decline despite increased fishing effort. Tourism suffered as underwater diving sites degraded beyond recognition. The Belgian coast, once renowned for marine biodiversity, became known primarily for beaches and seaside resorts, rather than underwater attractions. Scientists studying the problem identified the fundamental challenge. Marine ecosystems need structural complexity to support biodiversity. Natural reefs, whether coral, rock, or shellfish, provide three-dimensional habitat where organisms shelter, feed, and reproduce. Without these structures, most marine species cannot establish populations. The Belgian North Sea lacked the geological conditions for natural rock reefs to form, and centuries of oyster harvesting had eliminated biogenic reefs that once provided this complexity. Traditional artificial reef approaches had been attempted repeatedly with mixed results. Between 1985 and 2010, Belgium sank 23 decommissioned ships and deployed over 500 tons of concrete blocks as artificial reefs. Results were disappointing. The ships, while initially attracting fish, corroded rapidly in the harsh North Sea environment, releasing toxic metals. Concrete blocks provided minimal surface complexity. Their smooth surfaces didn't mimic natural reef structures effectively. Most critically, these structures were placed haphazardly without ecological design principles, resulting in limited colonization by target species. By 2015, marine conservationists concluded that traditional approaches were insufficient. Creating effective artificial reefs required fundamentally new thinking, structures specifically designed to maximize marine life colonization, built from materials optimized for the marine environment, and placed strategically to restore ecosystem functions. But designing and manufacturing such complex structures using conventional methods seemed impossibly expensive and time-consuming. Then, researchers at the Vrije Universiteit Brussels proposed something revolutionary, using 3D printing technology to manufacture artificial reef structures. The idea emerged from advances in additive manufacturing, technology that builds objects layer by layer from digital designs. What if this technology, typically used for manufacturing engine parts or medical implants, could create entire reef ecosystems. The concept seemed far-fetched. Critics immediately raised objections. 3D printing was too expensive, too slow, and couldn't produce structures large or durable enough for harsh ocean environments. But Dr. Els Verfeili, a marine ecologist leading the research, saw potential others missed. 3D printing offered unprecedented design flexibility. Unlike traditional manufacturing requiring molds and forms, 3D printing could create infinitely complex geometries. Structures with overhangs, internal cavities, varied surface textures, all optimized for specific marine species. Computer algorithms could design structures maximizing surface area and habitat niches while minimizing material use. Most importantly, designs could be tested, refined, and improved iteratively based on empirical results. In 2016, Belgium launched the North Sea Reef Restoration Project, a $5 million initiative to develop, manufacture, and deploy 3D printed artificial reefs. The project brought together marine biologists, materials scientists, 3D printing engineers, and commercial partners in an unprecedented interdisciplinary collaboration. The goal: demonstrate that advanced manufacturing could revolutionize ocean restoration. Timeline: 18 months from concept to first deployment. International marine conservation experts called it wildly ambitious and predicted technological failure. Development began with intensive research into reef design principles. The team studied natural reefs worldwide, coral reefs in the tropics, oyster reefs in temperate waters, kelp forests in cold seas, identifying common structural features that support biodiversity. They discovered critical patterns, complexity at multiple scales from millimeters to meters, varying orientations providing different current exposures, internal cavities offering protection from predators, rough surfaces facilitating organism attachment. Armed with this knowledge, computational designers created digital reef models incorporating these principles. Using generative design algorithms, software that explores thousands of design variations automatically, they optimized structures for maximum ecological benefit. The resulting designs looked organic, almost alien, branching structures resembling abstract corals, lattice frameworks creating protected spaces, surfaces covered with carefully calculated roughness patterns to facilitate barnacle and mussel colonization. Material selection proved equally critical. Traditional concrete, while durable, has high pH levels toxic to many marine organisms and lacks the chemical composition facilitating organism attachment. The team developed a specialized marine concrete blend, incorporating crushed seashells, providing calcium carbonate attractive to calcifying organisms, iron oxide, promoting beneficial algae growth, and carefully selected aggregates, creating optimal surface texture. pH was adjusted to match seawater, around 8.1, ensuring immediate organism colonization without toxic effects. 3D printing such large structures required industrial-scale equipment. The team partnered with Ghent-based company BigRep, which had developed massive 3D printers capable of printing objects over 1 cubic meter in volume. Even so, complete reef structures required printing multiple components and assembling them. Each reef unit consisted of 8 to 12 printed pieces bolted together underwater. Manufacturing proceeded slowly. Each reef unit required 48 to 72 hours of continuous printing, followed by 2 weeks of curing to achieve full strength. The first prototype, a 1.2 meter tall branching structure resembling a stylized tree, was completed in March 2017. Initial testing occurred in a seawater tank at the Marine Biology Research Station in Oostende. Within 48 hours, the structure was colonized by amphipods and copepods, tiny crustaceans fundamental to marine food webs. Within 2 weeks, barnacle larvae had settled and begun growing. Within a month, small fish were using the structure for shelter. The results exceeded expectations. The 3D printed structure achieved colonization rates 40% faster than natural rock samples in the same tank. Encouraged, the team proceeded to ocean deployment. Site selection was crucial. They chose areas within the Vlaamse Banken, offshore sandbanks that once supported oyster reefs but had been reduced to barren sand by trawling. These sites were now protected as special areas of conservation, under EU regulations, with bottom trawling banned, ensuring deployed reefs wouldn't be immediately destroyed. Water depth ranged from 12–22 meters, shallow enough for diver monitoring, but deep enough to avoid storm damage. In June 2017, the first artificial reef was deployed. Installation required careful planning. A specialized vessel lowered the 850-kilogram structure using a crane, guided by divers who secured it to the seabed with stainless steel anchors driven 2 meters into the sediment. Positioning was precise. GPS coordinates accurate to 10 centimeters ensured structures formed planned patterns, maximizing habitat connectivity. The first deployment took 6 hours of intensive work, exhausting but successful. Monitoring began immediately. Divers conducted weekly surveys documenting species colonization. Underwater cameras recorded activity continuously. The results were spectacular. Within 72 hours, amphipods and isopods, small crustaceans that form the base of reef food webs, had colonized the structure in densities exceeding 10,000 individuals per square meter. Within 2 weeks, barnacles and mussels began settling. By week 4, small fish, gobies and blennies, had taken up residence in the structure's cavities. The first month's results convinced skeptics. By September 2017, funding was secured for large-scale deployment. Over the next 18 months, 500 reef units were manufactured and deployed across 12 square kilometers of seabed. Each unit was placed strategically, with spacing calculated to facilitate larval dispersal between structures while creating habitat heterogeneity across the restoration site. The underwater landscape transformed from barren sand to complex 3-dimensional habitat. By 2019, just 2 years after initial deployment, the ecological transformation was undeniable. Species richness, the number of different species present, had increased by 320% compared to adjacent unrestored areas. Marine biomass, the total weight of living organisms, had increased by 400%. Particularly striking was the return of species absent from Belgian waters for decades. Native oysters, commercially extinct since 1995, began recolonizing the reef spontaneously. Larvae from distant populations in France and the UK, finding suitable settlement habitat for the first time in generations. The reef structures themselves evolved continuously. Within 6 months of deployment, they were completely covered by encrusting organisms, barnacles, mussels, algae, sponges, transforming the grey concrete into colourful living surfaces. This biological layer further increased habitat complexity, creating additional microhabitats for tiny organisms. After 2 years, some structures had accumulated over 200 kilograms of attached biomass, essentially doubling their ecological surface area through biological growth. Fish populations responded dramatically. Commercial species including cod, plaice, and sole, all severely depleted in Belgian waters, began appearing around the artificial reefs in increasing numbers. These weren't just transient visitors. Tagging studies revealed that fish were residing permanently in the reef complex, using it for feeding and reproduction. By 2021, fish biomass on the artificial reefs exceeded natural reference sites in southern England, a stunning achievement considering the Belgian reefs were entirely human-made and just 4 years old. The unexpected discovery that changed everything came in 2020. Researchers analyzing colonization patterns noticed something remarkable. Certain reef unit designs were dramatically more effective than others. Units with specific cavity sizes, approximately 8–12 centimeters diameter, attracted 60% more fish than other designs. Units with particular surface roughness patterns, ridges spaced 2 to 3 millimeters apart, achieved 80% faster mussel colonization. These discoveries revealed that tiny design variations had enormous ecological consequences. This finding revolutionized the project. The team immediately redesigned subsequent reef units, incorporating these optimization insights. Generation 2 reefs, deployed starting in 2021, incorporated refined designs based on empirical results. These optimized structures achieved colonization rates 150% faster than initial designs, demonstrating that 3D printing's design flexibility enabled continuous improvement impossible with traditional reef construction methods. The economic analysis revealed surprising cost-effectiveness. Initial projections assumed artificial reefs would never match natural reefs economically. But by 2022, calculations showed otherwise. Each reef unit cost approximately $8,000 to manufacture and deploy. Each unit supported an estimated 500 kilograms of marine biomass, generating approximately $2,500 annually in ecosystem services, fish production, water filtration, carbon sequestration. With reef structures lasting an estimated 50+ years, the return on investment exceeded 1,000%, making artificial reefs among the most cost-effective marine conservation interventions ever measured. Tourism impacts exceeded all projections. The artificial reefs became premier diving destinations. Divers traveled from across Europe to explore Belgium's underwater sculpture park. Dive operators reported that reef dives generated $5,100 per person in revenue, compared to $20–30 for typical Belgian coastal dives. Annual tourism revenue attributable to the reef complex exceeded $3 million by 2023, significant for a small project initially focused purely on conservation. Educational impacts were equally profound. The reefs became living laboratories. Universities across Europe established research programs studying the artificial ecosystem. Over 40 PhD theses have been completed on various aspects of the reef system. High schools brought students for underwater observation trips. The visibility of the project, with regular media coverage and public diving opportunities, raised ocean conservation awareness far beyond traditional marine biology circles. The technology continued evolving. By 2022, the team was experimenting with bioreceptive concrete, materials specifically formulated to encourage rapid biological colonization. New formulations incorporated oyster shell powder at 30% by weight, creating surfaces that oyster larvae colonize 3 times faster than standard marine concrete. Other variations included iron-enriched concrete promoting kelp attachment and calcium-rich mixes facilitating coral settlement. The latter intended for tropical reef restoration projects, learning from Belgium is success. Manufacturing advanced dramatically. Early reef units required 72 hours of printing. By 2023, improved 3D printing technology and refined designs reduced printing time to just 18 hours per unit, while actually increasing structural complexity. International adoption exploded. By 2023, 3D printed artificial reefs had been deployed in 25 countries across 6 continents. The Netherlands launched a $20 million program creating 50 square kilometers of artificial reef in the Wadden Sea. Denmark deployed 200 reef units in Kattegat. Even tropical nations adopted the technology. The Maldives used 3D printed structures to restore damaged coral reefs, finding that the precisely designed surfaces facilitated coral larvae settlement better than traditional restoration methods. The global 3D printed reef industry reached $50 million annually by 2023, with projections of $200 million by 2030. Multiple companies now specialize in reef manufacturing. Design software specifically for reef optimization has been developed and commercialized. Academic programs in marine engineering now teach 3D reef design as standard curriculum. What began as a speculative Belgian experiment became a mainstream marine restoration technology in less than a decade. Climate adaptation emerged as an unexpected benefit. As ocean temperatures rise and acidification increases, natural reefs struggle to survive. 3D printed reefs can be designed with climate resilience built in. Materials formulated to resist acidification, structures designed to maximize water flow and cooling, spatial arrangements creating climate refugia. Research suggests that artificial reefs may actually outperform natural reefs in maintaining biodiversity under climate change scenarios, a profound implication for global reef conservation. The philosophical implications are equally significant. For decades, conservation emphasized preservation, protecting existing natural systems from human impact. Belgium's success demonstrated an alternative: active restoration using advanced technology to rebuild damaged ecosystems. This approach does not replace preservation, but complements it. offering hope for degraded areas where natural recovery is impossible on human timescales. Challenges remain. Long-term durability beyond 7 years remains unproven. Will the structures last 50 years as projected? Monitoring reveals gradual degradation in some units, suggesting maintenance may eventually be required. Scaling to truly massive deployments, thousands of square kilometers rather than dozens, will require further manufacturing advances and cost reductions. Not all species benefit equally. Some specialists requiring very specific natural habitat features haven't fully colonized the artificial reefs, yet the trajectory is overwhelmingly positive. Belgium transformed 12 square kilometers of marine desert into thriving ecosystem in just 7 years. The technology continues improving. Each generation of reef units performs better than the last. Costs continue falling while ecological benefits increase. Global adoption accelerates as more nations recognize artificial reefs' potential. The North Sea, once written off as ecologically degraded beyond repair, now hosts pockets of remarkable biodiversity recovery. The underwater view tells the story most powerfully. In 2015, divers visiting these sites saw nothing but flat sand stretching in all directions, underwater deserts devoid of life. Today, the same locations reveal complex three-dimensional habitats, teeming with fish, crustaceans, mollusks, and countless other organisms. The 3D printed structures, now completely covered with living organisms, resemble natural reefs so closely that only close inspection reveals their artificial origins. This is ecosystem restoration at its most successful. Technology and nature collaborating to rebuild what was lost. Belgium's 3D printed reefs represent more than marine conservation achievement. They demonstrate human capacity to use advanced technology, not for exploitation, but for restoration. Critics said artificial reefs would never match natural ecosystems. Belgium proved otherwise. The technology that began as experimental prototype became proven solution deployed worldwide. What do you think about Belgium's 3D printed reef revolution? Could similar technology restore damaged ecosystems in your region? Share your thoughts in the comments below.